All right, guys, I think I finally got this going. It was quite redonkulous. My whole computer decided to just kind of wig out on me, so it took me forever to get back in. So, Calc BC kids, hi. I'm not sure. I think I have a couple viewers out there. I'm pulling up your guys' questions because literally everything decided not to work. So with that, if you guys have anything, I have my email up also. I already saw Aryan's answer to being patient. Thank you, Aryan. But if anybody else has a quick email you weren't able to get in questions that you had, that's totally fine. Just a quick reminder, there was already a live session last week. I think it was Thursday. So that one's recorded, that one's online. You can go ahead and just follow the link. And then, so if I refer to anything today being like, oh, hey, I already answered that question. Look, it's already been worked out. You can go ahead and, like, for instance, if I go quickly forward, you can see some of these have already been worked out. And so those explanations would be on a previous video, just a heads up. But I do have your questions. Sweet, a few more of you guys have actually turned them in. Aryan, you turned in some, and then Naomi, you turned in some. So let me go ahead and let's see. I think I have to, there we go. Issa's already went through. I'm gonna go ahead and start with Naomi's. Let me also pull up Aryan's. I have to look at them kind of separately, which is a little weird. Okay, individual Aryans. There we go. All right, Aryan, I see your first question as being number 12. Naomi, I see your first question as being number 2 and then 19. So let's start there. And we'll try to cover as many as we can with the time we have left. AB kids will be coming on around 8 o'clock, but we'll see what we can get done. So I have, let me go in a different color than I did the other day. So I'll do blue. Sure, why not? So we have number 2 from Naomi. We have number 12, I believe, from Aryan. We have number 19 from Naomi. Let's get the next page. Then I have numbers 28 and 29. 28 was already covered, but we can peek at it quick. Number 29, that was from Aryan. That was from Naomi. I'm not sure who's who, but that's okay. We have number 49 next on that one. Let's see if we have any ones before number 49. Number 40, 42, 44. I figure if I can just circle them now, that'll save a lot of time. So, oh, the proving ones. Aryan was talking about that today. We have 40, 42, 44, 48, 49. Okay, those were the same as Naomi's, I think. Let me do a quick undo. There we go. So 48 already done, but we'll circle number 49 too. All right, what else you guys got? Going down to number 62 on that one, this one, 48, 49, 57. Then 62. I did promise, guys, in the other video. Oh, no, that was for AB. Never mind. You guys are good. We didn't get to some questions on AB's last video. 65. What did I miss? 62. Good. We already got 70. And then that looks good for right now on that one. And that looks good for right now on that one. Okay, so let's get number 70, and then we'll go from there. I'm going back to the beginning. I'm going to go make sure really quickly that the video is still recording the right thing. Yeah, looks like it. Okay, if anything is weird, if you guys can't hear me, I mean, that'd be kind of hard, but hopefully you guys can hear me. Go ahead. And I see the little volume thing going. But if anything happens during the video, you can't see me all of a sudden or something weird wigs out, just pop me an email really quickly, and then I will be able to see that and fix it. So right now, number 2. Anyway, I got through my first day of in-service. We have 1 more week, then school starts. Hang in there, kiddos. Hopefully you can get some rest and have some fun before all the craziness hits. So let's go ahead and try to cover as many questions as possible. Let me pull this microphone as close as possible so that you guys can hear me better. Number 2, Find a value of y for which the line through A and B. So we have a line through 2 points. There we go. M is equal to negative 2/3. Let's be super cool and say, hey, we know the formula for slope. No derivative, nothing crazy like this. It's just a line. So the slope, we can do y2 minus y1 all over x2 minus x1. If you're wondering where I'm getting those from, I'm looking at these points as x1, y1, then x2, y2. And I'm using the formula of delta y over delta x. So y minus 3 all over 4 minus negative 2. We end up with negative 2/3, which is what they told us the slope was, equals y minus 3 all over 6. I'm going to do a quick little multiplication to get rid of that guy. Quick little multiplication. We end up with, let's see, 3 and 6, 1 and 2, negative 4. Equals y minus 3, which leads us, I believe, to y equaling adding 3 on both sides, negative 1. I'm going to really quickly pop over to the key. Keeps me honest. That way, if we make a mistake, I don't waste time. Perfect. Y equals negative 1. So if you're wondering what was going on here, it was using just that slope formula using these 2 points, x1, y1, x2, y2. Change in y's over change in x is equal to negative 2/3, and then solve. Okay, moving on to our next question, which I believe was at the bottom of the page, number 12. This one gives us a function x cubed minus 1. Remember this little f, negative 1, that's just the inverse function. Easiest way to find the inverse function is think of this f of x as a y value. Then we switch the x and y placements, and then we solve for y. So when we switch, we can go ahead and solve for y by adding 1. So x plus 1 is equal to y cubed. The only way to get rid of the cubed is with a cubed root. So we can say the cubed root of x plus 1 is equal to y. But remember, that y was just indicating, once we switch the x and y, the inverse function. So we could say f inverse of x is equal to the cubed root of x plus 1. It's kind of messy. I would flip the order there. But they were saying verify that, and this is all just one big, hey, the composition of a function with its inverse should reduce everything down to be just x. So if we were to check, if we were to plug in, I'll switch pens just to show you that I am checking. We would go ahead and for the first one, we would plug in the inverse, which is this guy. So we would plug in the cubed root of x plus 1 as the argument of the original. So we would need to cube that whole thing minus 1. That's us plugging in the inverse to the original. Cubed root cubed cancels out. But not just the cube itself, but the cubed root and the cubed cancel out. So we get x plus 1 minus 1 equals x. I'm going to put a little check mark. The rest of the answer, the rest of the solution would say, hey, go the other way as well. So if you guys notice down here, hopefully I went both ways. I solved for the inverse right here. Then I went ahead and plugged in and said, yay, it's x. And I went ahead and plugged in the other way and said, yay, it's x. And it worked out. So that was a long story short on that one. Remember, if I ever go too fast, you can totally come back to this a little bit later, slow me down, and check what I'm saying or how I'm saying it, etc. I'm checking the direction. Simplify. Look at this guy. Negative exponents. It's been a while. Simplifying, we get back to my blue marker. We are, I don't know, the way I explain it to AB kids, because they have some complex fractions also, is just think about these in 3 different categories. We have the constants, we have the x terms, or I should say the x components, and then we have the y components. So with all of that, if I was to look, first of all, just at the numbers, I could see the 4 and the 12 reduced to 1 and 3. So I'm going to put a 1/3. I'm going to go to my x's next. If you guys notice, this x has no power on his own, so we put a little understood 1. And whenever you have, for instance, an x to an a all over an x to a b, the property of like bases being divided is that we subtract the exponents. We would do x to the a minus b if you're just trying to simplify this little piece. And so what I see is an x to the 1 over an x to the negative 1/3. So I'm going to go ahead and say, hey, we can simplify this by doing x to the 1 minus -1/3. And then to deal with our y's, we would do the exact same thing. So y to the -2 minus a -5. This is a lot of simplifying. But what we end up with when we simplify that is on top, 1 is understood. X to the 1 plus 1/3 would be 4/3, right? Y to the -2 plus 5 would be y to the 3 all over 3. I guess we could rewrite that. We could say something like that's 1/3 x to the 4/3 y cubed. We could write like a cubed root in there with the x. I can double check real quick what the answer packet showed for number 19. Oh, I did the same thing. 1/3 x to the 4/3 y to the 3. So what you didn't get to see in that answer key is my explanation of, oh, hey, like bases, division, you subtract. If it was like bases multiplication, then you add the exponents, but division, we subtract. With that, we go down to number 28, 29. Number 28, there was a formula from pre-calc. It's in the yellow highlighter. I explained not so much where the formula came from, but like, oh, hey, this is the formula that you do need to use for the problem. So it wasn't something I expected you to have memorized or to remember. You could have found it in your pre-cal notes if you had those out. But otherwise, it's totally fine if you steal that formula and then just from the problem realize how to plug things in, or check and see if you can plug things in, like the n in the formula that you see 2 different places down here and up here was from how many compoundings per year. When they say quarterly, that's 4 per year, which is why I threw in a 4, etc. So once you have that formula, see if it makes sense why everything got plugged in where it did. Let's go ahead and peek at number 29. Oh, this is what you guys meant today, the pi over 5. Okay, if it was just cosine of 17 pi over 5, we would not be able to find it. Not exactly, not without a calculator. It'd be impossible. But it's not just cosine of 17 pi over 5. It's cosine inverse of cosine of 17 pi over 5. So cosine inverse and cosine. Normally we say, oh, sweet, they cancel each other out. Cosine says go forward to a ratio. Cosine inverse says go backwards to the angle. Going forwards and backwards usually ends you in the same spot. But here's the problem. Cosine inverse has domain restrictions. Dun, dun, dun. So here's what I'm going to do. I'm going to take 17 pi over 5 and say, where does that land in the unit circle approximately? I'm going to think of 17 pi over 5 as a mixed number. So I'm going to think, okay, 17 pi over 5 is the same thing as 3. Hopefully I don't do bad math on here. And 2/5 pi. So if I'm thinking about my unit circle, I'm going to go 1 pi, 2 pi, 3 pi, and then I need to go 2/5 pi, which is a little bit less than half. 2.5 is half of 5. 2 is a little less, so it's going to be somewhere in the third quadrant. Okay, Mrs. Regan just texted me. I should probably turn my phone on quiet. Okay, so 3 and 2/5 pi, or 2/5 pi. So once again, I went 1 pi, 2 pi, 1 pi, 2 pi, 3 pi. That was really confusing. Let me do that one more time. I'll go forward a little bit so that you can keep my picture. 1 pi, halfway around, 2 pi, all the way around, 3 pi, keep going, and then 2/5 pi. Ends me somewhere here. Now that might seem kind of inconsequential. How does that help me at all? It's not one of the special unit circle values, but what I can think of is, wait a minute, cosine inverse wouldn't let me go around the full unit circle and then keep going. It only allows me to think basically in between 0 and 2 pi. So my question is, what would 17 pi over 5 be in the 0 to 2 pi range? Well, if you look at it, another way of going to that exact same angle location could be just going forwards, which would be 1 pi going here, and then plus the 2/5 pi that we just talked about. So then that would end up being 1 pi, which is 5 over 5 pi, plus 2 over 5 pi. We can say that this is the exact same angle, 17 pi over 5, which in essence, in a way, is canceling out the cosine inverse and the cosine, but keeping it within the domain restriction. 17 pi over 5 is, in a sense, going to translate to 7 pi over 5. Another way of arriving here could have been to take that original 17 pi over 5 and subtract the the 2 pi, that it's too big, or that it is, it's a coterminal angle. So you could take away 2 pi to go backwards in time, sort of, which would be 17 pi over 5 minus 10 pi over 5, hence once again 7 pi over 5. So cosine inverse cosine, in a sense, cancel each other out, going back to the angle, but 17 pi over 5 was too big, had to fit between 0 and 2 pi. So we figured out what is this exact same angle location, taking away 2 pi, making a common denominator. Or another way of thinking about it is just kind of logically in the sense of, okay, I'm going to go pi, and then I'm going to go that 2/5 more, and then we could have just done 5 over 5 plus 2 over 5. But sorry, that's probably just beating a dead horse. It's just explaining the same thing multiple ways. Hopefully one of those helps. Good news is, quiz on summer packet isn't going to be until Wednesday, next Wednesday. So Monday is a lot of logistics. You guys know the first day of school, passing out books and syllabi and 0 period stamp sheets and all that jazz. But we should be able to go over a couple questions, like in class, live, you guys explaining what's discouraging. Better way of saying that, what's still confusing at that point. And then Tuesday, we might go a little bit more over questions, but then we're going to start on notes. So you're going to have a little bit of time to come after school if you still are confused on something after today. We're jumping down to number 40, T-proof, one of my favorites. Ironic, it's one of Mrs. Regan's favorites, and she just texted me. I don't know. But, oh, she was checking on our first day back because we missed her and she missed us. Okay, I'll be quiet now. Don't tell her I told you that. We are supposed to be proving that the left-hand side matches the right-hand side. If you guys remember anything about T-proofs from, I don't know who's watching this, but Aryan, I know you were with Mr. Che. T-proofs, long story short, always choose the more complicated side because that's the one that we can play with more. So I'm going to go ahead and choose that side. I'm going to try to make the left match the right. And the very first thing I see, the denominators do not match. So I'm going to first of all go ahead and try to make common denominators, multiplying this guy top and bottom by the other guy, sine, and then multiplying the other guy top and bottom by this guy, 1 minus cosine. So I'm going to go ahead and say sine squared theta, once again multiplying by sine, over sine. Sine squared theta is on top, all over. I'm just going to leave this factored because my hope is that I don't need to multiply this in, because that's really nasty if I do have to multiply it in. I'm going to go over to this side. My pre-cal kids, yes, this should all be right here underneath after rewriting. We did have proper form, but the sad thing is there's not a lot of room to fit that in. I guess I could zoom in. We're not doing that. Okay. The other one, we're going to multiply by the other denominator, hence the 1 minus cosine theta. Remember, we're multiplying by 1 creatively, so we have to have the numerator and denominator match, or else we're throwing everything off balance. I see the sine theta times 1 minus cosine theta on the denominator. I have like denominators. That's nice because I can now go ahead and put them together, but the dilemma is I have to think about that numerator. The numerator right now, I don't really think I want to just write 1 minus cosine theta squared, because that doesn't help me put these guys together once I come to this step right here. So instead, I'm going to say, well, if I want to square the 1 minus cosine of theta, I can. You might not have thought of doing it, but you can multiply those two together just by foiling or by some trick with perfect square trinomials. I'm going to go ahead and multiply quick. We're going to get 1 minus 2 cosine theta when we combine the outer and inner like terms, plus cosine squared theta. And some of you might be like, this is not looking at all like what it's supposed to be. It's supposed to be 2 cosecant theta. But check it. You guys look, isn't sine squared plus cosine squared really just 1? Dun, dun, dun. And 1 plus 1 is 2. And 2 minus 2 cosine of theta all of a sudden has a common factor we can pull out, which is the 2. Now, before you know it, it's just a little bit of simplifying using that sine squared plus cosine squared is 1, and 1 plus 1 is 2. And there are now 2 minus 2 cosine of theta, 2's in both that we can pull out. We can now go ahead and simplify the 1 minus cosine of thetas, and we have 2 over sine, which is 2. Oh. Secant. It's not magic, it's math. Dun, 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 dun. Love those, but they can be so frustrating if you can't see which direction to go. Common denominators was the name of the game. Okay, number 42. I was waiting for this question, and I was surprised Isa didn't ask it. Number 42 says, determine the range and find the max and min values of f, stating where those values occur. Here's the dilemma. This is a quartic. And with quartics, do we really want to factor this guy and find the intercepts, the zeros? The answer is no. To find the max and min, we would need to go back to basic graphs, which I know it's a quartic, so it's harder than most. But with the negative quartic, it's going to be either like a parabola upside down, or it's going to be one of those funny like upside down W things with the 4 branches, 1, 2, 3, 4. So the dilemma is not knowing exactly where he is. What we can say, though, is that the maximum value would need to be at one of these peaks. And the minimum value is going to be none. That one's easy, because this is going to go to negative infinity. So there is no minimum value, just knowing what a quartic looks like and a negative quartic that's headed down. It's either a parabola or it's kind of a skewed parabola. Now here's the dilemma. In order to find the maximum, we would need to find our critical points. So as we go to find our critical points, we'd have to find our first derivative. I know technically calculus shouldn't have shown up yet on the packet, but you know calculus. So instead of worrying about factoring this nasty guy and finding like the halfway, like if you found 2 zeros, finding the halfway and that's going to be at the top, or maybe finding these zeros or those zeros and finding halfway points, that's just going to be disgusting. That's pre-cal. We know how to do calculus now. So the first derivative ends up being negative 20 minus 2x minus 12x cubed, which looks great and all until we say, oh, you know what? We want to set this guy equal to 0. Because we need to find the horizontal tangent lines at the maximum values and figure out, okay, is it only 1? So that's the max, or are there 2? And we have to compare. So here's the dilemma. We need to factor a cubic. I mean, I can pull out right now, what, a negative 2? And I get, let's rearrange this to make it nice. I would get a 6x cubed plus x plus 10 equals 0, which is great and all, until you figure out that now we have to find the zeros of this guy. Last year, it was super nice in that if the zeros were something like a cubic or a quartic or a quintic, it should be a nice number that we would plug in. For instance, check out x is 0. Oh, that doesn't work. Never mind. Check out x is 1. Oh, wait, a positive plus a positive plus a positive. That's not going to work. X equals negative 1. Oh, sweet. This might be better. Negative 6 minus 1 is negative 7 plus 10. Well, dang, that's a positive number. That's not good. We could plug in x equals negative 2, which would end up getting us negative 2, 4, negative 48. Minus 2 is negative 50 plus 10. All of a sudden, I'm in a negative. Now, here's the struggle. Intermediate value theorem. In order for a quartic, a polynomial, which is a continuous function, to go from a positive to a negative, it had to cross through a 0. Here's the struggle. Is there a nice 0 in between negative 1 and negative 2? And the answer is no. No nice 0 in between negative 1 and negative 2. What's that mean? This is a decimal 0. What's that mean? We would need to use our calculator. What's that mean? Well, life sucks. Maybe we shouldn't have solved this by hand. If you guys look at the answer key, I graphed it on my graphing calculator. Hence why I said use the graph to find. I know it sucks, but there are no nice zeros. These are nasty ones. This would not be on the AP non-calculator graphing section. This was just a, hey, graph them and say where the max and min are. No, no, no. Don't find where the max and min are. Find the max and the min. The min is none. Once again, it goes to negative infinity. But the max, well, the max is at the point negative 1.139, 29.434. But remember, when it asks you for the max value, let's improve upon the answer in the answer key. The maximum value of the graph is going to be a maximum value of 29.434. Remember, if you were to write it in a sentence, at So the value of the y value at the x value, negative 1.1. That's the best way to write it. But anyway, I'll stop being picky. Long story short, there we go. That's the max. And I don't even know why I wrote the range. Oh, because it says determine range. Anyway, use the graph. Lo siento if you were struggling on factoring that guy for a long time. Let me do undo. Get rid of that nasty mark. And let's keep going to number 44. Aw, you guys don't like conic sections? Come on, party poopers. Just kidding. It's a circle. I was able to find the max and min, but I was confused on finding the range. Oh, okay, so Aryan, for the range, sorry, I had a quick clarification on the last problem. Let me go to the answer key just to explain the answer on that one. So for the range, remember range are the y values. Domain X, range are the y values, domain are the x values. For y values, we just need to think of the y-axis, which goes from negative infinity. Writing a y is really hard right now. Negative infinity to positive infinity, and look at the function itself and say, basically, here's how I would explain it in pre-calc. How low does he go? How high does he go? How low does he go? Negative infinity. And that's why I lead off there. How low to how high? He starts at negative infinity. And how high does he go? Or I should say, how low does he go? He doesn't really start, but he goes to negative infinity, and then how high? That point, the y value, 29.434, and that's how you get the other part. So it's an interval from how low to how high using the y values. Hopefully that makes sense. Let me pull back up my email so I can see if anyone else has emailed. But how low to how high? Arian, if they were to ask for domain, remember we're thinking how left to how right if we're using something like a graph to figure it out. That moves us on to number 44 in the circle. I mean, I don't know. First thing when I think circle, and granted, I remember a lot more pre-cal than most because I teach it year after year, but y minus k, no, let's not use that one. Let's do x minus h quantity squared plus y minus k quantity squared equals r squared. That's the standard form, the conic section form of the circle. Nice thing is if you guys remember that standard form of the circle with translations included, the HK is the center of the circle, the R is the radius. The cool thing is that you could go ahead and get the equation of this really quickly. Consider the circle of radius 5 centered at 0, 0. That would be the equation x squared plus y squared, x minus 0 squared plus y minus 0 squared equals 5 squared. That's the equation. That's the function that we're looking at. And then it says find an equation of the line tangent to the circle at the point 3, 4. Well, go team. Tangent, we need a derivative. Derivative, we have a function. We just need to find that derivative implicitly. And so I would have found the derivative by taking the derivative of x squared, taking the derivative of y squared dy dx equals derivative of any constant is 0. That would lead me pretty quickly to dy dx is equal to negative x over y after simplifying or reducing those 2's. We could go ahead and plug in the point they told us 3, 4, so such that we have the point 3, 4. So we know that the derivative, which is the same thing as the slope of the tangent line, so we could say m is equal to slope of this tangent line we're supposed to be finding, negative x over y, so negative 3/4. We have the slope. We already have the point, so if they just want that in according to the direction slope-intercept form, I'm just going to go ahead and do good old point slope form, y minus y1 equals m times x minus x1. And once we have all of that, then we can go ahead and just move everything to one side. I don't think I'm going to take time to do that, but let's peek at it really fast. Oh, I am so sorry. I was super lazy and stopped where I would have in class. I stuck it to the man. Slope-intercept form, all they're asking technically is us to go ahead and keep going to y equals mx plus b, which we would be able to do if we were just to get y by himself. And you could do that by distributing the negative 3/4 and then adding the 4 to the other side. It gives us something exciting to check on the first day of class and see if you simplified that right. It's multiplication and addition. Don't be afraid of the fraction. Okay. With all of that, let's go ahead and go to the next question. Maybe it would have been faster if I just simplified, but that's okay. I have to leave something for you guys to do. Number 49, just kidding. You've worked hard on the summer packet. Keep working, keep attempting, grading, trying to correct. Number 49 asks the age-old, even, odd, or neither, that I know most, many if not all, of you don't like doing. But if you look at this function, it's just a sign that's been translated up one. So I don't know, the easiest way, if it's something like in number 48, that was not an easy one to visualize. Like, what the crap does that look like? I don't know. I mean, ultimately, it's kind of a line. But anyway, that's nasty to visualize. But 1 plus sine of x, I mean, take your normal sine curve, which hopefully you guys kind of remember, right? Starting at the origin, repeating every 2 pi, and shift him up 1. So shifting him up 1, I apologize, it actually should hit at 0. There we go. So it was at -1, now it's at 0. If you guys look at that, it doesn't have to be even. I know we have to review some things. To be even, it needs to have y-axis symmetry, which means what's on the left of the y-axis is what's on the right, like a butterfly folding. That's up and that's down. That doesn't work. Nope, so no. Odd, origin symmetry, the origin, specifically this point right here. So what's up and to the right of the origin better be down and to the left of the origin, and no, it doesn't work with it being shifted up. It's no longer symmetric about the origin. Since it's not symmetric about the origin, forget that, it's not odd either. So last but not least, it's neither. That doesn't mean that sine in and of itself doesn't have symmetry, but when you shifted it up, it no longer has odd symmetry. Don't worry, brain farts happen to all of us. So I think the graph is the easiest way to go on that one. Number 57 says, hey, guess what? These things called sigmas, yeah. Summation notation, yeah, we have to review that a little bit. Don't worry, we'll review it in BC when it comes to it again, but this was just kind of a pre-cal thing, having you guys and go back if you needed to go back, or maybe Google it, or just try to scratch your brain a little bit, how these work. You have a lower bound, you have an upper bound. Kind of like an integral, or I should say an integral is kind of like a summation, but you start at the lower bound and plug in for n, so 0 squared over 4. These are called summation notations because they're sums, they need adding. So 0 squared over, I apologize, I almost made a big old mistake. 0 gets squared over 2 according to our pattern. Then we have to go ahead and say, now go from 0 to 1. You count by integers, 1 to 2, 2 to 3, 3 to 4. And we stop at 4 because that's our upper bound. That's where we need to stop. That's our upper limit. And so with our upper limit, we can go ahead and plug in and say, sweet, we have 0 plus 1/2 plus 4 halves plus 9 halves plus 16 halves. You might be like, she's dumb. Why didn't she simplify 4 halves and 16 halves? Well, guess what? They're all halves. So 1 plus 4 is 5. 5 plus 9 is 14. 14 plus 16 is 30. 30 divided by 2 is 15, I think. Am I going too fast? Paranoid about the time? Nope. Got it. Go team. And so the only difference on B, I'm not going to go through it, is that you start at 1, end at 3, plugging in 1, then 2, then 3. See the sums right there, put them all together. And then you end up either with something nasty like 1 plus an 8 plus 127, or you get nice common denominators, you're welcome, and then get 251 over 216. Don't get a decimal. That's nasty. Just say no, unless it's a calculator section. But then you should not be simplifying. Anyway, let's go to number 62. Limits. Limits. Basic graph, ln. Basic graph, ln. ln of just x. Remember, he has a vertical asymptote at 0, which is why the domain for that is x greater than 0. There's that vertical asymptote at 0. So what happens when all of a sudden now you have a -5 on the inside? That is called, my dear friends, a horizontal shift. When it's on the inside, it's opposite what you think, to the right 5. To the right 5. So horizontal shift to the right 5, guess what shifts right 5 as well? Not just the graph, but also the vertical asymptote. So new graph of that ln is going to look like, for this guy, 1, 2, 3, 4, and 5. From 0 to 5. There's no like vertical, horizontal flipping or stretching or any of that craziness. It's just going to be an ln shifted 5. So why does that make all the difference? You have that graph, then you just need to think, what is the limit? What is x approaching as I come from the right of 5? Well, hopefully now it's pretty obvious. Coming from the right, I am going to negative infinity. Coming in towards 5 from the right, following the graph, negative infinity. So therefore, final answer, negative infinity. If you're coming from the left, we'd be in big trouble because there's nothing there. So that would not exist. But coming from the right, yeah, graph comes from the right and it goes down and down and down and down. 65. Well, maybe I should make a forever card out of this. Maybe it would just save people time. Long story short, we can actually, just say the final answer is 3/2. Yay, magic. No, there's math behind it. Let me show you the math. If you guys plug in 0, remember real quick, you always should plug in first. And when you plug in, you get 0 over 0, which means keep going. But how? Using algebra? No, using L'Hopital's. Ooh, that would be fun. Using L'Hopital's would be super nice because using L'Hopital's, we would get the derivative of sine as cosine of 3x. Don't forget derivative of the inside. Don't kill a bunny. Chain rule. Derivative of 2x is 2. Now plug in. Cosine of 0 is 1. 1 times 3 is 3, and 3 over 2 is 3/2. That's the cheater way. Not keeping going with algebra, but instead keeping going with L'Hopital's. If you wanted to do it the algebra way, you would have to remember this old-fashioned forever card. The limit as, maybe it's not all that old-fashioned, as u goes to 0 of sine of u over u is 1. You're like, but the answer's not 1. Well, because these don't match yet. But with some creative math, we could fairly quickly make them match. We could do the limit as x goes to 0. We haven't taken it yet. Of sine of 3x, and we could say we need a 3x, but all we have is a 2. Well, you can put in a 3 if you multiply top and bottom by it. So if I multiply top and bottom by 3 over 3, a little bit of creative transformation, can I say that? You end up with sine of u over u. That part will go to 1. And what's left is 3/2 times 1, which is 3. So either we can memorize this little limit as u goes to 0 of, I'm trying to make it way too general. Limit as x goes to 0 of sine of ax over bx will always be just a over b. That's actually going to be true. L'Hopital's, I think, is a much easier way because you guys know that they don't have to necessarily give you one that looks just like this. Hence why I don't try to have you memorize specific types of problems. But that is a quick shortcut that probably some AP people, kind of like the SAT people, try to have you do tricks. That could be a trick to simplify life a little bit. All right, I think we're getting pretty close to the end of these, which is good because I'm supposed to be switching to AB. AB kids, if you just joined us, sorry, my computer was having some serious malfunction, so BC got cut short like 20 minutes. But I think I'm almost done at the end of their questions. If you want to just leave the video going, go get a snack, go get some carrots or, I don't know, nice coffee. Or don't do that. You won't have time for that. If you want to grab something real quick and then come back in a couple minutes, we are almost at the end. Calc BC kids, where are we at? Just number 70? And then you guys are champs, or you haven't finished the packet. But good news is, this is the last page of the packet, and so Isa's questions went all the way. You better not have questions on that. Isa's questions went all the way to the end, the nasty parametric polar review stuff from pre-cal. Actually, Calc AB kids, if you're tuning in, all that stuff from the end of last year comes back in BC, but you won't have to face it this year. Anyway, so some of those already got answered. Maggie, I know that you said one of these derivatives got gross, but you do have my work that you can check out for the answer keys. Let's stop at number 70. AB kids, hang in there. The very last question on the BC packet that I need to cover. Number 70, find an equation of the tangent line. Ding, 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 ding. I need a derivative to the hyperbola Okay, don't get confused by them saying hyperbola. I mean, they're telling you what it is, but whatever. You just need to find the equation of the tangent line to that function at this point. Don't stress about the hyperbola. It's not super important. What's important is, can you, y minus y1, you can do that quick, equals m. Oh no, I need a derivative. X minus x1. How do I find the slope? No big deal. You've taken Calc AB, BC kids. Let's just take a derivative, and the derivative of, now some of you, I know, you hate taking this derivative. Use the quotient rule, do what you gotta do, but for others of you, just make it x to the -1, power rule. Bring down the -1, you have y prime is equal to -3 x to the -2, which you might remember, sorry, puts it in that denominator. We just need to find the specific slope, and to find the specific slope, let's plug in this point, aka when x is equal to or such that x is equal to 3. So plugging it in, I don't know, my quick math, -3/9 ends up being -1/3. Could you put it in slope-intercept form? Sure, why not, but stick it to the man. I don't see any directions telling me to do that. Checking, sorry, the answer key real quickly, number 70. Sorry, randomly marking on my document. Y minus 1 equals -1/3 x minus 3. Dun, 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 dun. BC kids, we did it. Woo! I don't see any new emails, so I don't see any new questions that popped up during the video. Some of you might have been like, dang, I should have had my packet attempted to ask the questions that I had. Well, remember, we do have like a day when we get back before the quiz on Wednesday. So have your questions ready then. If you want to pop me a quick email, maybe I can try. Remember, this answer key is there with my work on it, but I know it doesn't have explanations. Get through as much as you can as far as the problems that you get wrong, trying to find the corrections. You should be doing those in color pens, BCers. You know the drill. Do what you got to do. Reach out to friends, have a study party. I heard a couple of you guys talking today. That might be a great idea. If you watch this BC video, either now currently live or at a later time, and you are going back and watching it, you do need to prove to me that you watched it, and the best way to do that is the following: a random email. Just kidding, it's going to be specific. I need you guys to email me and just say live study session number 2 completed. Live study session number 2 completed. I believe it's the name of the video. Live study session number 2 completed. And then I need you guys to go ahead and write the phrase. Let's see, what's the phrase? Last time it was Mr. Rogers. This time, let's go ahead and do my dog is licking his paw. There you go. That's very original because that's literally what he's doing. He's distracting me right now. So you can go ahead and send me an email of BCers. You've watched the video. You got some questions answered, hopefully. Live study session number 2. You can just put the random phrase, my dog is licking his paw. Chap, I guess, has a dirty paw. Anyway, and that will be proof that you watched the video, because how else would you come up with that? Don't just randomly give your friend the phrase. That's dumb, and you just lost your integrity. All right, BC kids, sign out. See you guys later, hopefully on Monday. Hopefully you're not one of those that comes late to the first day of school. That would be sad. ABers, it's your turn. Bye, BCers. Okay, ABers, I have your guys' summer packet questions up. I have a lot more responses than last time. Thank you, thank you, thank you. I'm going to go ahead and just go through kind of in order. Some of these we did go ahead and cover last time. Sorry, you're looking at my iPad screen, which is all over the place. Let me close out BC notes. Let me open up AB. There's the AB summer packet. Get rid of the BC. Last time on the AB summer packet, we did not get to finish everything at the end. So I promised the kids who were on the last video, because they were keeping track, I promised them that I would work through the questions backwards. So if some of you guys are like, I have so many questions at the beginning. Well, there are two different things for you to try. First of all, I'm getting my answer key to the end of the packet. I apologize if that's making you dizzy. We're going to start, if you're in your packet, on limits, which is the very end of part 1. These are the ones with the videos. I think I sent out an email today. The videos that have not been working for you guys, it was by this individual dude who probably didn't upkeep his website, kind of like some of you guys. I'm sure you've seen apps that haven't been updated with new operating systems and they just become obsolete. I think that's kind of what's gone on with these guys' videos. So we're going to go over the questions that people had. here at the end of the packet. We'll work our way backwards. And if you're like, you're not covering my specific questions, well, remember, there's a whole nother video that I recorded last time. There's a whole nother video that I recorded last time. And that whole other video, I'm trying to get to my screen to make sure you guys are seeing what I'm seeing. Good. Went over a lot of questions. For instance, just look really quickly. I've saved all of the work from that video. So all of these that you see red and green and highlighted and blue and whatnot, all of that was written with my explanation on the first video. So if I skip something today, and if it's something that already has some work on it in the packet, the reason I'm skipping it isn't because it wasn't asked, it's because it was asked and it was answered in the first video, just so you guys all know what's going on exactly. With that, here we go. We're starting on limits. We're starting on the very end of the packet. And then if some of you guys haven't tuned in yet to a live session, you're going to have to kind of do what BC did and hang in there through the chat. Shush. Now he's pawing at the blanket, but no, that's not what you're supposed to be emailing me. You're supposed to be listening. Towards the end of the broadcast at some point, I will go ahead and give you your own unique phrase, your own unique email to send in. And then if any of your friends were not able to tune in tonight live, you can tell them, oh, don't worry, read the email, you can go back, you can watch it, and you can get credit as well. Okay, here we go. Limits. Let me get my questions up. Sorry, I lost them momentarily, but I'm getting them back. All right, right here towards the end of the packet, the first questions that I had you guys asking were under limits number 7. Let me go ahead and circle just a few so that way, let me change the color of the pen today. That way we can kind of tell the difference. I have questions on number 7. Then not again until numbers 10 through 12. Oh yeah, these are some of the specific ones. Not again until number 16. Oh, this is circled from last time and I didn't get it. 16, 19, 22, and 24. Let me see if I missed any other ones. 16, 19, 22, 24. Okay, good. So we're going to cover those ones first. Then we're going to go to a little further in. We have a question on number 26, number 27. It's a bummer because I made these questions specific to these videos because they were really cool in the sense of kind of keeping it basic. Khan Academy, like I emailed you, has great information. You just kind of have to dive in a little bit. The nice thing is in this summer packet, I do try to give you like a quick little teaching moment with a few different rules and see if you guys are able to use the rules. Once again, don't worry. It's not like you're going to come in the beginning of the year, you better know this or else, and then I just zoom past it and say, well, we're moving on. We are going to go ahead. I'm going to go back and I'm going to reteach the limit section. I'm going to go ahead and also reteach the basic derivative rules, the intermediate value theorem. This was to see how much you guys could get on your own. That way, when you come in, it's more of a review and less of a, oh, I'm seeing this for the first time and maybe not getting as good of a grasp. Sorry, the last two questions that we have here at the end, number 39, 42, and 44. Thank you also for those of you that added your responses to, or your questions to the Google Doc. That helps me a lot as far as knowing what to go over. All right, so let's go ahead and start with number, sorry, not this page. There we go, number 7 on limits. Let me go back to my video screen so I can see what's going on. All right, so the very first question that I see is right here, number 7 on limits. We're looking at a graph. That's what's right below. So it says for the following graph, find. These two different, let me zoom in just a little bit. These two different problems, you can kind of think about this as, for instance, like this being a little letter 7a and this being like a little 7b. Two separate questions, but with the exact same graph over here. We could call this function f of x if you were confused. We're looking at this function. He's a piecewise function. If you heard the sigh, that is, once again, my dog being loud and bored. Anyway, it's a piecewise function in that we have one linear piece coming up to this x equals 3, which is breaking the function. At x equals 3, for x greater than 3, it now goes into what seems to be this parabolic function. It could be exponential, it could be something else. But it seems to be linear all the way up until, let's see, x less than or equal to 3, and then this parabola. But we don't have to write out a nasty piecewise function to find the limit. We just need to remember, let me zoom in for just a second, what this notation means. It was in our pre-cal notes at the end of last year. This notation means what happens when we have a little plus and what happens when we have a little minus. Whether you looked at con to review, whether you looked in a you don't have a pre-cal book. The The little plus sign means, and the way I would say it from last year, is coming from the right. You could also, some people would say from above. Remember, here's our x equals 3. So from the right are from all of these x values down here. When x equals 5, which is up here on the graph. When x equals 4, which is up here. When x equals 3.1, which is up here. 3.01, 3.001. What's going on as the function comes towards 3 from above? Well, I see it on this parabolic curve. It's getting closer and closer and closer to what height, what destination, if we're talking about the guys in the diner? 1. It's getting closer and closer and closer. It doesn't matter, remember, it doesn't matter whether or not the diner is locked or open, whether the diner is burned down or there. What matters is the height that's being approached. Move. And the height that's being approached on this first one from the right is 1. So that's my limit, looking for y value answers. But for the other one, now all of a sudden I'm not coming from the right, now I'm coming from the left. That's that little minus sign. Denotes, some people would say from below. So we're coming from the x values that are below 3. We could think of at 1, well, if x equals 1, we're up here. If x equals 2, we're up here. If x equals 2.9, we're up here, 2.99, 2.99. We're on this line, and as the line comes in towards x equals 3, where is it getting closer and closer and closer to? I don't care if it's filled in. I don't care if it's empty, but what height is it getting closer and closer and closer to? Seemingly 3. Dun, 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 dun. Coming from the right, coming from the left, and looking at the y values as the answers. The next few questions down here, when it says, how do you evaluate limits? We might not have in regular pre-cal gotten to all of these answers as far as like seeing examples of each. In honors, I think the notes are still up for honors. I don't think I've deleted them. Well, the videos are definitely still on YouTube on my channel. I think the notes are still technically saved on my website. If you guys want to peek in honors, and then that might be easier than even Khan Academy in answering some of these, because honors we went a little bit further. But substitution method is what I would have called last year the plug it in method. And I know that regular and honors got to the plug it in. And you can use substitution method basically as long as the answers exist. So as long as, I would say, as long as the function is continuous. Sorry, I'm writing cursive because it's faster, but the function is continuous so that we don't have that nasty like piecewise thing like up above problem going on. ABers, by the way, if anything weird happens during the video, if my mouse just stopped working, if you can't see anything, if the sound just randomly cuts out, if you have a question in like I answer and you would love to further like ask some more clarification, just send me an email. I have my Gmail opened up and I can go ahead and see that and I'll try to answer. That's the easiest way to comment because I don't think you guys can be signed into your Heritage Warriors as you watch this. So don't ask me why. I don't know. It is what it is. But long story short, I apologize, coming back to the question at hand. As long as the function is continuous, not a weird piecewise one, and the answer exists, then we can always plug it in to solve for a limit. Basically, when does it not work? You could give a couple counter examples. If you plug in and get 0 over 0, hopefully some of you are like, keep going, good. Because the answer is not done, but you're just not quite there yet. 0 over 0, keep going. Or number over 0. Or DNE. No, it's not me, it's my dog drinking. Oh my goodness, it's so loud. But 0 over 0, number over 0, or DNE. If you plug in and get any of those answers, then those are counter examples. Plugging in did not work. When can you use the factoring method? This is the factor and cancel or factor and simplify, if you want to think of it that way. Factor and simplify. This is when you have, I should say when factoring is helpful. When you have a rational function, you want some sort of fraction, otherwise factoring and trying to cancel doesn't even make sense. So a rational function, some sort of fraction, where plugging in results in 0 over 0. The time when we want to factor and try to cancel, or cancel, because it should work, is whenever we plug in and get 0 over 0. Rational function, Plugging in gets 0 over 0. And more specifically, you could say something like you have a polynomial numerator, I'm abbreviating, I apologize, and denominator. When you have a polynomial numerator and denominator. The reason I'm saying that is right down below when you can use the conjugate method. Once again, all three of these were at least shown in the honors pre-cal notes if you guys want to go see examples covering limits last year. But the conjugate method, you're going to do that when, once again, you have a rational function, you have a fraction. Once again, plugging in, you get 0 over 0. But this time, instead of having polynomials on top and bottom, you're going to have square roots. Well, it might not even be square roots. Let's just go ahead and say radical expressions. Not as in really cool, as in having a square root. Radical expressions in the top, aka in the numerator and or denominator. It might be numerator and denominator, might just be the denominator, might just be the numerator. But anyway, you can see some examples down below. For instance, no one asked on these, so that means that you guys must have been able to kind of figure them out. But this one, if you plug in, you do get 0 over 0. And it's like, oh no, keep going. Well, we're going to use the conjugate method because of that square root. Conjugate method says multiply by, keep it the same, the part with the root, just change sign. Keep the binomial the same. Remember, what you do on top, you have to do on bottom. So we're not even looking at that guy at all in the sense of multiplying. Keep it the same, but change the sign, and you would go, and that would help you transform to be able to get an actual answer. This one, plugging in, works just fine. There's no 0 over 0, number over 0, DNE. Just plug in, you're done. This one, you plug in, once again, you get 0 over 0. Keep going. And how do you keep going? Factor that puppy. Hopefully it'll cancel out with the denominator, and that is that factoring method of number 2. So actually, if you guys want to think about it, if you were able to solve 13, A, B, and C, you can kind of just look at those functions and describe them for 10, 11, and 12. So for number 12, that's like what is necessary for A. For number 10, that's what was necessary for B. And for number 11, that's what's necessary for letter C. Okay, I've definitely covered that more than I meant to. Let's go ahead and pop up to horizontal asymptotes. We talked about that in pre-cal. We talked about it in a basic way. And then in honors pre-cal, at least maybe regular, we talked about it with limits. Long story short, horizontal asymptote, what we're doing is looking at the, you could say end behavior. That's one way that we talked about it, the end behavior of the function. Another way of saying that is looking to the right. What's the function do as it continues to go to the right? Or you could also say to the left. Sometimes it's the exact same thing. But you're trying to figure out the end behavior as you look to the right, as you look to the left. That's just kind of like how you look at the function itself. But a horizontal asymptote will occur or will exist when the graph levels off. And levels off at some sort of y value, some sort of horizontal line it gets closer and closer and closer to. However, that's looking at a graph. And that could be how you answered it, and I wouldn't necessarily say that you're wrong. But if you're looking at a function, it doesn't actually say a function's graph, it says a function. You're looking at an equation. Here's the struggle. When we talk more about limits, we'll say in order to go to the right or to the left, we're going to have the limit as x goes to infinity, positive infinity, or the limit as x goes to negative infinity of a function. But we don't even need that, to be honest, to answer this question. What we need to say is, well, how do we know when a horizontal asymptote exists? And this is going back to pre-cal. Because in pre-cal, we learned how to do those limits to infinity. We learned how to figure out horizontal asymptotes by looking at degree tests. And the degree test, this would have been first semester, chapter, was it second semester? Degree test, I think it was polynomial functions, chapter 2, maybe, end of 1. 1 is a long chapter, like 10 sections. It was chapter 1 or 2. But degree tests, horizontal asymptotes will only exist when the top and the bottom, remember, just silly ways of saying numerator and denominator, are tied. So when the degrees of the highest exponent of a term, when the degrees are tied, AKA you have like a quartic on top and a quartic on bottom, and it's like, oh, sweet, ratio of the leading coefficients. Yes, the horizontal asymptote exists. Or if the bottom wins. You guys could clarify on this. You could go into deeper explanation as far as what happens with the ratio of leading coefficients when the top, bottom, numerator, denominator are tied in their degrees. You can go with more depth when the bottom wins. Then you're going to have a horizontal asymptote at 0. I don't remember exactly what I did as far as the answer key. Oh, I just said limit as x approaches infinity and negative infinity. I guess I was just saying what to look for. And you're looking to the right, to the left, the end behavior, limits to infinity and negative infinity. You guys could have gone into more depth for sure. I wasn't actually talking about the answers on this one. I was just talking about, I guess I should say the video was just talking about trying to tie in horizontal asymptotes to limits at infinity. Oh well, sorry I went into too much depth. I could help you though on like 17, 18, 19, 20 if you had any questions. Speaking of which, there is a question on number 19. So this should help us out. It says if the degree of the denominator is less than that of the degree, less than that of the numerator, that's the case, bottom wins. And whenever the bottom wins, looking at a rational function, the degree of the bottom being greater than the degree of the top, you are always going to have a horizontal asymptote at y equals 0. The function is going to level off, and it's going to level off closer and closer to the x-axis or the y equals 0 line. The next kind of question down, or I should say the next question down below is number 22. Number 22, different teachers, that's the struggle with the Khan Academy versus the video I originally had you guys looking at, might define this a few different ways. So let's just peek at the answer key on this one and see if they make sense. According to, maybe not Khan, he does most of his videos for calculus, maybe not according to Khan, but according to how I'm going to be teaching this year and according to the videos that you guys weren't able to see, there are 3 different types of discontinuities. I don't mind if you just grab the names right here from the answer key. There's point discontinuity. Something's wrong at just the point. Infinite discontinuity. There's some sort of asymptote, and specifically a vertical asymptote. So it's, in a sense, the function is going infinitely off. And then a jump discontinuity. So the point discontinuity would just be a hole. Infinite discontinuity is going to have a vertical asymptote. And a jump discontinuity is going to have pieces of a piecewise function, typically is what we're talking about, that don't match up. Jump discontinuity, pieces of a piecewise function that don't match up. And remember, continuity. Continuity, to simplify it, we're going to have to get more precise in our language in calculus. But generally, continuity, just think of, as I'm drawing a graph, what would make me pick up my pencil in drawing? Well, a hole would make you pick up your pencil, or it should. A vertical asymptote would make you pick up a pencil, and so would a jump discontinuity. An easy way to tell if a function is continuous, well, I mean, easy as in a pre-cal way would be what I just described. So you might have just gone there and been like, oh, hey, if you have to pick up your pencil. But what they were trying to explain is if you try to find a limit using the substitution method, long story short, if finding a limit, if plugging in doesn't work. If plugging in for finding the limit doesn't work. If you get 0 over 0, if you get number over 0, if you get a DNE, there's something wrong. You might not know which of the 3 types, like from up above, but if you plug in to find a limit, they would call it the substitution method. That's what up above called it. If it doesn't work, there's some type of discontinuity. Now we're over to the intermediate value theorem. Ironically, in pre-cal, we covered intermediate value theorem. Oh, man. Definitely not at the end of the semester, of second semester. We covered this, I think, early on in first semester. But you just couldn't, in pre-cal, get a very deep understanding of the intermediate value theorem. But what we said in pre-cal was basically intermediate value theorem. Intermediate, in between, not beginning, not advanced in math. Intermediate value theorem, in between value, y values. It's basically saying if a function is continuous, if you can draw the function without picking up your pencil and having to put it back down, if a function is continuous, then to go from one height, one y value to another y value, you're going to have to somehow cross through all the in-between y values, intermediate values, in-between y values at some point. So the struggle in number 26 is you're like, what graphical illustration are we talking about? Well, I think, I might not have written this illustration on, oh, I didn't. Okay, so you have no idea what that is. Give me 1 second. And D, you look at the answers to see what the D and C go with. C. Okay, long story short, let me go ahead and just draw what this picture would look like. You have a function, you're going from an A to a B. The intermediate value theorem, you could have found that on Khan, you could have found that by Googling. It says there must be some value C such that the function would need to go through from f of A to f of B, all in between values D. Let's do that. So we can call this a function f of x. And so what the intermediate value theorem would say in words, in order for the function to go from f of A, that would be this guy, to f of B, from one height to another height, on some interval A to B, there's going to have to be some x value C such that f of x is equal to D. So it's a little confusing. I'll be able to expand on this a little bit more in class. The long story short is in that paragraph or that sentence that gives you the intermediate value theorem. If you did any sort of calculus definition or written out statement of that theorem, you should have seen a C. The C specifically is talking about the in-between x value. And we're trying to locate the D, which is the in-between y value. So don't stress too much. You guys didn't get to watch the particular video that I meant. So the answer to this would have been a bit trickier, definitely, for you. The sad thing is in number 27, that was a great illustration that doesn't really help you out in the sense if you didn't get to hear his explanation. But what it was saying was, she was trying to do this whole like losing weight sort of thing. She started it on October 2nd. She finished it on October 28th. Oh, fat project. Actually, she was trying to gain weight. I totally forgot that. But she was trying to gain weight. But if you guys look at here, the long story short that I can tell just really quickly by reading my explanation was that as of October 2nd, she must have started a little bit earlier. She'd already gained 6 pounds. That's how much she gained, not how much she weighed. That would be really weird. Nicole would be like a baby. But then on the 28th, according to this information really quickly, she had gained 22 pounds. Once again, she was trying to gain. It was some sort of weird project that she was a part of, probably got paid for. Sadly, you get paid to ruin your body. But anyway, October 2nd, she had gained 6 pounds. October 28th, she had gained 22 pounds. So they say, hey, was it guaranteed that she gained 26 pounds? According to the IBT, there's no guarantee for that because all we know is that she's lost 6 and she's lost 22. And IBT says, okay, she must have lost everything in between. She must have lost everything in between, which means at some point, at some day, at some time, had she gained 18 pounds? And the answer is definitively yes. Why? It makes sense. Yeah, that's true. But what's the mathematical theorem that explains why it makes sense? Well, the intermediate value theorem. Gaining weight is a continuous function. You can't randomly go from gaining 6 pounds to gaining 10 pounds by not weighing all the in-between weights in between. I said in between twice. It's okay. In between, intermediate might help it stick. But apologize once again. I mean, we already know this section is based on videos that we weren't fully able to see. So apologies on that. Let's go forward to number 32. Sweet. We're almost done with this section, so we can move on before the end. Number 32 says the power rule. let me go ahead and just kind of work through this. I know the answer key probably has some. Some of you just need to hear me talk it through. The difference quotient we definitely saw last year multiple times. I'm sure there are explanations videos trying to work on that one. It's kind of tricky. A lot of you guys don't like the delta x. A lot of you guys instead would like to make, let me change how I write that. You would like to take that delta x and say, ew, gross, can we make him h instead? And yes, definitely we can make him h instead. So let me go ahead and change this real quick. Let me do the limit as h approaches 0 of f of x plus h minus f of x all over h. You're going to like that a lot better. Remember, whenever you see this of, f of, that means we're plugging in. F of, we're plugging in. F of, that's all talking about the inputs. So this function up here that I'm supposed to be plugging into, f of x is x squared. All it says is take the input and square the input. So f of x plus h. Who's my new input? X plus h is. So x plus h is who is getting squared. F of x, well, only x was getting squared. And then all over h. We saw last year whenever you plug in, now we're plugging 0 into h because of how the limit is set up. Not 0 into x, but 0 into h. Whenever you plug into the difference quotient, it always, 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 always will give you 0 over 0. It's an impossible problem trying to find a slope of a tangent line, a slope given 1 point. But with the limit, remember, the impossible becomes possible. We approach it instead of going straight there. So whenever you get 0 over 0, no stress. With the limit, you keep going. And how do you keep going? It looks polynomial-ish. So if you were to FOIL out this expression, FOIL x plus h times x plus h, you would get x squared plus 2hx plus h squared. You still have the minus x squared. And just a few of you might have remembered, hey, I think things are supposed to cancel out. And they most definitely start canceling out. Next thing, we're going to go ahead and reduce because there is an h on the bottom. And both the terms up top, 2x plus h, those h's are going to go ahead and reduce away. Remember, we keep rewriting the limit until we finish the limit problem. And so there at the very, 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 very end, now we can go ahead and say, hey, let's take this 0. Let's plug it in for h. And what we end up with is 2x plus 0. No more limit. We're taking it. 2x plus 0 is 2x. That is solving for a derivative using the definition of the derivative, aka the limit of the difference quotient. So I worked that one out. The work is, I promise, on the answer key as well, and probably a bit prettier there because I wasn't using my iPad to write it. And then there are these really cool basic derivative rules that I think almost all of us at some point, it might have been really quick for regular pre-cal, saw the power rule, which is a really, really, really cool shortcut. There are other cool shortcuts as well that let you basically avoid this big old nasty definition that you guys saw at the top. And so I just wondered if you guys could use some of those shortcuts. One of those shortcuts is called the quotient rule. Ironically, under the quotient rule, it actually, number 39 was asking you for 2 of the basic derivative rules. It wasn't actually making you do the quotient rule for number 39. It was asking you to fill in a couple basic ones. And some of you were like, well, that stinks, except one of them was right here on the other page. One of them was right here. Derivative of cosine is negative sine. So if they asked you for the derivative of cosine, which they did, you could have just looked back there at that, what you will come to know as a forever card. You could have just filled in and said, oh, sweet, that one's written on the card. Dun, 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 dun. And then, knowing that calculus is a class that is very, it's common in all high schools, not that tons and tons and tons of people, not that the majority of students take it. That's not true. It's definitely an achievement. It definitely takes a lot of work to be able to even take calculus. But there's a lot of calc kids out there. You could have very easily just Googled, hey, what's the derivative of e to the x if you hadn't been able to find it. But I'll help you out. The derivative of e to the x, he's the weirdest rule ever. The derivative of e to the x is himself. And there's a really cool quote about that, but you don't get to hear it until we start covering that in Calc AB. Here in number 42, Number 41, you would have already answered the question that the chain rule is necessary or needed in composite functions, in compositions of functions where you have an outer and an inner, and maybe like an inner of an inner. Some of you might remember last year when we had to decompose functions. We had to take something like a square root that had a cosine in it, that had a 3x squared minus 1 in the cosine, that had a, like it was one of those where we were trying to figure out who's the innermost and peel it off layer by layer. That's when the chain rule is needed. And this is a fairly basic chain rule problem. Khan definitely has chain rule videos to give you an introduction. Once again, we'll definitely be covering this in a lot more depth in class. Just seeing what you can get on your own for a first time through. As you guys look at this, f of x is equal to sine of 3x. There is an outer and there's an inner. I'm going to go ahead and show the outer with my yellow highlighter. So here's the sine, and then there's sine of. The outer is the sine of 3x. The inner is the 3x. Normally, we just have sine of x, or sine of u, or sine of theta. We don't, usually I should say, the most basic function of sine would not have a 3 in there. So if we're looking at this, we could technically go ahead and call the inner function 3x. And we could call the outer function sine of, a couple different ways of doing it. We could go ahead and say sine of u, and we could let this one be called u. So the outer function is just sine of something. And it's like, sweet, sine of who? I don't know, u. And then you actually look at it and say, okay, who's the something inside? Oh, u is 3x. That's one way of looking at it. There are different ways. One guy who does a video online calls it blop. The outer would be sine of blop, and then the inner would be the blop, which is 3x. But the long story short of the chain rule, if you were to find that rule, if you were to find that formula, if you want to make it super technical, you could call the outer function f of x. You could have named this sine of x instead. You could name u g of x, and that might help you if you did find a very technical formula for the derivative of the chain rule. It says f prime of g of x times g prime of x. Some of you might have found that rule and you might have been trying to use it and gotten confused. Others of you might like the words better. The derivative of the outer. I'm just going to put deriv instead of derivative. Derivative of the outer, keeping the inner as the argument, times, so that's the f prime of keep the g of x inside, times the derivative of the inner. If I can actually keep writing, there we go. And how this plays out in this example, derivative of the outer, derivative of sine. Going back and looking at that forever card, the derivative of sine is cosine of who? Of x. No. Keep the inner. Who was inside sine of 3x? 3x was. So cosine of, keep the 3x. He doesn't change. He stays the argument, but we're not done yet because we still need times the derivative of the inner. And the derivative of 3x using the basic power rule would just be 3. And you would end up with 3 cosine of 3x. Now, if this doesn't make total sense, it is okay. The chain rule is rough. And that's why we're going to have a section on it. And that section, I think, lasts probably like 3 days, maybe even 4. So don't worry. There's a lot to the chain rule, but this is just giving you an introduction. I think the last question that we have here at the end is number 44. Go team. If you guys notice, I actually did give some very specific Khan Academy videos that kind of narrows down even a little bit better as to which ones you can look at. In the email, I kind of gave you like which categories, but this one actually gives you which videos. Number 44. Number 44, I know, on the video, some guy worked it out, and that would have been really nice. But sadly, you guys can just watch me work it out, or I don't know if I worked it out in the answer key because I didn't need to. Oh, I did kind of work it out. But the example got changed. Oh, dear. All right. So let's go ahead and keep it with this because you weren't able to watch the video anyway. I think he updated his video and changed the example a little bit, which is why I had to change that. But it's okay. You can just watch me You can watch me work it out. So the derivative of f of x equals e to the x over cosine of x. This is what we call the quotient rule because there is a division. There's going to be a top and there's going to be a bottom, a numerator and a denominator. The quotient rule, if you guys watch a video on it, or if you look at the rule, says when you have a numerator and a denominator, the quotient rule goes like such. I call it bottom d top, or keep the bottom, keep the denominator times the derivative of the top. So keeping the cosine the same, the derivative of the top, or e to the x, is still e to the x, minus top d bottom, or keep the top the same. Derivative of cosine, as we just wrote in a second ago, is negative sine of x. So keep the bottom, derive the top, minus keep the top, derive the bottom, all over the bottom squared, which would be cosine of x quantity squared. In the video, he gave them like 4 different possible answer choices, said, hey, try it, and then I'll show you how to do it. So that's why I said circle which answer choice you chose first. Don't really stress about this per se, because you weren't even given the opportunity to choose 4 different answers. But just instead write out the solution for how to solve this problem. At this point, we would go ahead and rewrite this to make it a little bit nicer. The e to the x is shared on both the first term and the second term on the numerator. So I'm going to pull out a common e to the x. I'm going to have cosine of x minus the negative would be plus sine of x. All over, don't get tricked by the trig notation. Cosine of x squared gets rewritten as cosine squared of x, which leads us to, sadly, nothing can really cancel out because there's no cosine that's shared in the numerator that can come out and be reduced with the denominator, so you kind of just get stuck right here. But that would be the final answer. So we have covered all the questions at the end, the ones that maybe on the Khan Academy videos you guys were a little bit stuck on. So thank you for all of those questions, both the old and the new. We were able to get through that. I'm going to go ahead and just keep working my way backwards because we definitely spent more time last time at the beginning of the packet. So I'm going back to the questions that have been submitted. I'm just going to go over the ones that had the most people submit it if we didn't go over them yet. Because we still have about, what, 15 minutes? Okay, so I am working my way backwards. So going before limits right here to simplifying expressions. It's the 90s, 90 to 97. I had a lot of you guys ask number 90. I've already answered that one. 91, 92, 93, 94. Okay, I had one person ask on 95, 96, 97. Let me do one question from down here. I don't think these ones were covered last time. If someone wants to send me a quick email, if there's one in particular that you want to see. Otherwise, I think number 95 kind of looks worse to me. I'll give you a couple hints. Like on 96, I would say, what's the common denominator between 2 and 4 and 8? I would choose 8. So I would multiply my nifty trick. I would multiply top and bottom by 8. You can think about it 8 over 1 if that makes it a little bit easier on your head. You can just keep these. Remember, keep them separate. You can multiply 8 over 1 to the 1/2 to the 5/4. That's what I would do. It's probably what I did in the answer key. 97 you probably don't like because you could pull out a negative to make it x minus 5. That's the key step before knowing how to simplify with the x minus 5, x plus 5 factors down below. But 95 I think is a bit grosser. Number 95, sorry, I was meaning to do a different color for all of these. Oops, there we go. Number 95, when you raise a power to a power, 4 is just to the 1. So 1 times 3/2 would just be 4 to the 3/2. Power to a power you multiply. So a is going to be to the 5/3 times 3/2. Now to simplify this, the a is kind of easy because you just reduce the 3's and you just get 5/2 left. The 4 is a little bit harder in that this can actually be simplified pretty well. Now you could remember, this exponent, fractional exponent can be rewritten as 3 becomes the power of the 4 and the 2 just indicates which kind of root you're going to use. But with that still gets kind of tricky, as in there's a lot of math and simplifying to do. I think I would like a little bit better to say, okay, the 3/2 is great and all, but the 4 can become a 2 squared. And if you change the 4 to be a 2 squared, now power to a power, you have 2 squared times 3 halves. You can think of it as 2 over 1. Maybe you can figure out that that's going to end up, the 2's cancel. You get 2 cubed, a to the 5 halves. 2 cubed is 8. 8, a to the 5 halves. But some of you are like, 4 cubed wasn't a big deal. So back here, I wouldn't have minded doing 4 cubed square rooted. And maybe you would have been fine. 4 cubed is just 64. 64 square rooted. It's going to get you to the exact same place as I got. So both ways are good. Depends on how complicated the problem is as to which way maybe you would want to go. But that at least covers one more in that section that a lot of you guys had questions on. I'm moving backwards, remember once again, and I'm going back to complex fractions. Here's the bummer on complex fractions. I have one question on every single one, which is a bummer. Last time I did these 3, well, I guess I did number 87. I think we only had questions on 85, 86, 87. So someone new submitted a question on 88 and 89. For sake of time, I'll do one of them. Remember, once again, there were some hints given, or all of number 87 was solved in the first video, the first live session. Just looking at this, I'm going to do number 88 for a couple of reasons, but the main reason is because there are 2 different denominators, 2 different stuck denominators, 2 different baby denominators that go ahead and make this a complex fraction. Using my trick that I've, apologize, my dog just messed up the email, there we go. Using my trick from last year, the different denominators that I see that are stuck is both x and x plus 1. Both x and x plus 1, multiplying top and bottom, putting those parentheses to not forget the distribution. Remember, we're taking this to both the first and the second. I think I have time just to go ahead and show this clearly. You're going to have x times x plus 1 times the first term, which would be x over x plus 1, minus. You're going to have x times x plus 1 times the second term, which is 1 over x. So right now, just working through the numerator being multiplied. Then you have a big old fraction bar. Now working through the denominator being multiplied with this distribution once again. This x times x plus 1 needs to be multiplied by x over x plus 1. Then it also needs to be multiplied by 1 over x. And if you notice, do things cancel out? And the answer is yes. So the x plus 1s cancel in this first term. The x's, I should say reduce on this term. The x's reduce here, the x plus 1s reduce there, and the big, long story short, is what is left. In the numerator, I see an x squared as what's remaining in this first term. I see an x and an x, so an x squared. I see a minus, and then I see just an x plus 1 times 1, so minus x plus 1. Don't forget those parentheses, don't kill a seal. In the denominator, I see an x squared. Instead of minus, I see a plus x plus 1. And so pretty quickly, you guys are able to see that. There's the x squared, and then the plus, then we have x plus 1. We can pretty quickly, hopefully, simplify that to be x squared minus x minus 1 all over x squared plus x plus 1. You guys could try to plug in, or I should say, I apologize, factor to see if that reduces. The bottom is actually unfactorable. That's impossible. So nothing's going to reduce with the top. So we would just go ahead and leave it. I can get back to my document. There we go. Leave it just like that. And there we go. So that's another complex fraction example. Before that, even and odd functions, we didn't have as many questions, which is good. I think we covered the majority of these in the first video. We talked about number 77. We talked about number 82. We talked about number 84 and answered both of those. Number 83, I'm not going to really explain it besides the fact of, hey, this is really just a sine function shifted up 4. And so if you take a normal sine function, let me do it in a dotted line. Normal sine function starts at the origin, cycles every 2 pi. If it goes up 4, then this height, 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, going up 4. 1, 2. That's going to go ahead and shift right up there. So is this one. The middle is going to shift one below that. Each of the middles are going to shift one below. Then each of the low points, these ones, are going to shift even one below that. So you can kind of just see it here. And the reason I'm drawing this graph is because as much as is possible, I like symmetry looking at a graph. And there's only going to be symmetries one of two ways. Well, I guess three ways. Either going across the y-axis symmetry, which is even, or across the origin. So either across the origin or across the y-axis. Or you could have x-axis symmetry, but that would be a non-function. So if you guys look at this graph right here, what's on the right side of the y-axis and what's on the left side is not a perfect copy. One's up and one's down. So right away I can say that y-axis symmetry is out, aka this is not odd. Then origin symmetry, looking next to see if, I apologize, y-axis symmetry, this is not even. Then looking at the origin and saying, oh, okay, so what's up and to the right of the origin should be down into the, no, there's symmetry, but the symmetry is all up here in the graph. The symmetry is not at all around the origin way down there. So therefore, this does not have origin symmetry either, even though sine is normally odd. And this one, once it got shifted up, or similarly, if it would get shifted down, it will not have y-axis or origin symmetry. That's covering the symmetries. The nice thing is we work backwards from here. The questions kind of just get fewer and fewer logarithms. We covered 69, we covered 73, we covered 74, we covered 76. All of those were covered in the last video. That's properties of logarithms. Going back, we did have a couple questions added in the first logarithm section, which would have been number 63 and 65. So I can go over those quickly. This is simplifying logarithms without a calculator. Dun, dun, dun. Some of you hopes were crushed, and I apologize. But long story short, how to simplify logarithms without a calculator. The easiest way, I thought we talked about this last time, but log base A of A is always 1. Ln of E is 1. Log base 7 of 7 is 1. Log base 3 of 3 is 1. So if we were able to change this up a little bit, maybe, just maybe, we could actually simplify using this cool little property from last year. So let's start with the easiest one out of the two that were asked. You might not think it, but number 65 is actually the easiest one because ln has a base of e and I see an e. Now it's in a denominator, that's true, but I can actually rewrite that 1 over e to be e to the negative 1. And once I rewrite that as e to the negative 1, if you don't remember who ln is, I can rewrite him as what his definition actually is. It's log base e of e to the negative 1, which means that negative 1 property of logarithms can go ahead and come down ultimately in front is a silly way of remembering it. And you would have negative 1 times log base e of e, which is, right, like the property shows up above, 1. You end up just with negative 1 as your final answer. Similar to if, in number 49, just quick, even though it's not written here, if you were to rewrite 27 as 3 cubed, log base 3 of 3 cubed would just be this remaining 3, which would come down. I apologize, that looks like an 8. It was meant to be a 3. Okay. But that 3 remaining is from the power. Same thing here. This little negative 1 ended up being our answer because it could pop down. Now, 63 is weird. I totally agree. He's kind of nasty. Let me kind of build backwards on this one instead of getting too abstract and too weird. We might have a couple of these in class that I talk about at much more length, just kind of trying to help you guys. See if this makes sense in your head. Can you get 8? I know, it's going to kind of come out of nowhere. Can you get 8 by multiplying 4 times the square root of 4? Can you get 8 by multiplying 4 times the square root of 4? Hopefully your answer is yes, because 4 times the square root of 4, 4 times 2 is 8. The reason I like, or I'm trying to show you that 8 can be rewritten as this 4 root 4 is because all of a sudden now I have everything in terms of 4. Now, I can't quite do like we did in 59 or 65 and go straight to the answer, but what I can do is I can go ahead and rewrite this and say, well, hold on, can't I make a square root a fractional power? So can I make it 4 times 4 to the 1/2 power? I'm going to get rid of this little arrow that got in the way a little bit down here. And once I have that rewritten as 4 times 4 to the 1/2, I can go ahead and say, hey, when bases match, if I'm multiplying, I can add the exponent. So technically, this is the same thing as log base 4 of 4 to the 3/2, or 4 to the 1.5. And all of a sudden, dun, 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 3/2 can come down. Log base 4 of 4 is 1. And the final answer is 3/2. I know it's out there. I know it's a little bit creative. You've seen things like it before, but it was back when we were working on logarithms and spending like days on different sections and learning these properties really well. This would have been one of the trickier types of problems. So 3/2 is the final answer because that is the power of 4 that equals 8. That was covering the logarithm section. Going back exponential, let me make sure I see multiple questions on number 56. Okay, that's a new one that we didn't get to see before. Right away peeking at this, solving, I'm like, oh, I want these bases to match for the 1-to-1 property. And I say, I think I can get back to a power of 3. Like 9 is 3 squared. It's in the denominator. I can make it a negative power to the x. 27 is 3 cubed. So I can change 27 to 3 cubed with that 2x plus 4 on the outside. And once I rewrite it like that, I'm like, oh, I'm so close. I want to go ahead and make it 3 to the power of, okay, power to a power you multiply, -2 times x. And then over here, when I go ahead and try to simplify, once again, power to a power you multiply. This is a little weird because it has a little baby binomial. So I'm going to end up with 3 to the 6x plus 12. And all of a sudden, now 1-to-1 property, as soon as these bases match, man, golden, we're ready to go. -2x is equal to 6x plus 12, at which point we can go ahead and basically rearrange. Long story short, check out the answer key. I think we should end up with -8x equals 12, x equals -3/2. I might have done that way too quick. So make sure you go check out the step-by-step if you haven't gotten there. But I think you subtract the 6x, which would be -8x, divide both sides by -8, which would be -3/2. Okay, there you go. Double check that out, though. There are multiple questions on that one. Number 54 on horizontal asymptotes. People didn't like that one at all because horizontal asymptotes, you kind of have to go 2 different directions. In this specific example, because this square root of x squared can either be a positive x or a negative x. So when you go to compare the degrees, and remember, when comparing degrees for horizontal asymptotes, take the strongest one. The strongest one up top is the -3x. And the strongest one on the bottom is that square root of x squared, but sometimes that can be a positive x, and sometimes that can be a negative x. Now hold on, pause. I am not writing equals. I am not saying that this function is equal to that function or equal to that function, but I am saying that as you go to infinity and negative infinity, this function will act like that one eventually and act like that one eventually. They're going to be very, very, very similar eventually. I'm just doing my degree test. And as I do my degree test, just looking at the highest degrees, ultimately the x's, the powers, or the degrees are tied. So I can take the ratio of the leading coefficients. And this first one's going to have -3 as the ratio of leading coefficients. But the weird thing is with this special example, because of the whole plus or minus square root dealio, is going to have not only at -3, but also another one at y equals +3. And go ahead and check it out. Graph this function and see. And as you go to the right and as you go to the left, it levels off, but in 2 different ways. It levels off at 3, going one direction, and -3 going the other. Our time is, I know I'm 2 minutes over, but I apologize. I know you guys were actually shorted by about 5 minutes of BC kids questions. So I'm peeking real fast to see if there's any other one good one. 46 we covered last time. That was asked by multiple people. Transformations of functions, number 43, we covered last time, asked by multiple people. Number 40, good, we covered last time. So all the ones that have the most questions, as far as I can tell, as far as multiple ones of you being confused, 2930, check, check, 3435, check, check. Some of you that added your responses, I don't think you had checked out the video yet from last time. Sorry, checking out real quick. Number 24, yeah, we did that one already. Number 20 and 21. Okay, we didn't do number 20. Let me see if there's anything else where there are more questions being asked. Number 15. Hang in there just a little bit, guys. Remember that you still need to hear from me how to prove that you watched this. And then last section is functions, number 11. Okay, so I see really quickly number 11 and number 20. Those are going to be our last two for today. So starting in number 11 real fast. Composition of functions. Remember, you need to be plugging in. So what I see right here is g of h of x cubed. So looking at h, first of all, the x cubed needs to go into the h. So right now, h has just an x that's being put in. That's the input. And the input gets squared. So when I go to solve, I can do g of, I'm going to get h of x cubed by taking h's argument, which is something squared minus 1. Plugging in x cubed, which is what I saw right up here. I still have to deal with that g, but I'll do that in just a second. So I have g of x cubed squared is power to a power you multiply. 3 times 2 is 6. Now all of a sudden I see, okay, so now I need to go ahead and plug what into g? I need to plug x to the 6th minus 1. So what is currently in g? X. What's the pattern of g? 2 times the input plus 5. That's the pattern of g that I see up above right here. What's going into that input? X to the 6th minus 1. I'm going to let you guys go ahead and simplify by distributing and combining like terms, but that's how you would want to do number 11. And last but not least, number 20. Just to see if I can give you a hint. Find a domain and range. Nice thing is this is one of our big old domain problems, square roots. Any even-powered root, you take the inside of the root and say, you're not allowed to be negative. X plus 3, you have to stay positive or 0, greater than or equal to 0. Can't be negative or else you're undefined. So the domain's pretty easy. Subtract the 3, you get greater than or equal to negative 3. Dun, 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 dun. Domain, range. Oh, range. In calculus, we're going to try and get way better at having just a natural, quick understanding of graphs. Like, for instance, this one is what we would call a radical graph that you guys saw last year. Normal square root of x, just plain old square root of x, starts at 0, 0, and just concave down, goes up forever. This one, however, has been shifted to the left 3. As we can see here, everything went to negative 3. So we could say it's been shifted 1, 2, 3. However, it's not just been shifted, well, it has been shifted to the left 3, that's true. But instead of going up like the normal one does, up in a concave down fashion, this one also has that negative in front. So it's going to be going down. You guys could, I suppose, double check me on your graphing calculator, but we are going to get, once again, better at being able to do just quick sketches of these, not tons and tons of points. And if you guys look at this range, how high does he go and how low does he go? Well, how high does he go? He doesn't go any higher than y equals 0. He doesn't go any higher than the x-axis. How low does he go? Negative infinity. So if it's in inequalities, I would just say y is less than or equal to 0. Now here's the problem. It says interval notation as our answers. So I know I'm running out of room, but I write a little bit bigger on the iPad. So for the domain, if x needs to be greater than or equal to negative 3, there's a bracket at negative 3, and x is allowed to go up to infinity. That's going to be the interval for x. And for range, the interval for y is allowed to go up to 0, but it's not allowed to go past 0, but it is allowed to go down to negative infinity. Some of you guys might need to review interval notation just a little bit. Once again, it's one of those other topics that we are going to review as well. in a sense of, in the summer packet, I mean, there are a lot of things that we're not going to be able to review a lot, like complex fractions, even, odd. But when it comes up, we will review them quickly. The summer packet was just to get you an introduction. I have quite a few of you guys that are on here. I'm not sure how many of you guys have been on here the whole time, but hopefully at least a few of you guys got most of your questions answered that you had. I was able to get through, I think, the majority of the new ones that were added. And once again, if I did not talk about your question in this video, it's probably because it was on the one before. And that's why some of these answers will be in red and some of them will be in blue. If you guys have a specific question that you're totally stuck on and super frustrated with, go ahead and pop me an email. I can try to answer it. But once again, we will have a day and a half when we get back. Monday, part of the day after logistics, and then Tuesday, the quiz isn't until Wednesday. You guys can pop in my room Monday or Tuesday after school to ask me specific to you questions also about the summer packet. But remember, you have to have it attempted, graded in colored pen, and then go back over what you get wrong and try to correct with the answer key first, and then with the live study sessions second. If you need both, cool. If you only need one, awesome. If you don't need any, watch one to get your 100% participation. In order to prove that you went to this study session, I know it's not perfect. I'm asking you to use your integrity as well, but please email me live study session 2 completed. Please email me live study session 2 completed. And the weird random phrase I'm going to have you guys put, what is my dog currently doing? If any of you guys are here at the beginning of the video, he's doing the exact same thing, ironically enough. So let's not use that phrase because that's going to be the same as BC. Instead, let's use cooler weather is coming. we hope and pray. So email me live study session number 2 and the phrase cooler weather is coming. At least we hope and pray. You don't have to add that last part, just cooler weather is coming. And I will know that you came on here. Kiddos, enjoy the last week before school starts. Let me know if you have anything in specific. Anything specific that I can answer as far as questions that you have with calculus at the beginning of the year. If you have scheduled questions, that's totally Mrs. Pratt's, not me. Hope you guys get some rest, have some fun before the craziness starts, and I get to go back to work tomorrow and today. Anyway, go team. I'll talk to you guys later. Email me if you need anything. Once again, live study session number 2 completed. And then cooler weather is coming. If you email that, you have your participation. All right. If your friends did not watch this tonight, and if they randomly say live sessions, what live sessions, and they're in calculus, tell them to go back, tell them to watch them, because they need to get participation as well. I'm signing off. Happy Monday. See you guys later.